Hi, welcome back to Unit 10 of AP Physics C E&M. This is, again, electric circuits. So in the last video, we kind of laid the groundwork for this video. In the last video, we talked about electric circuits, what they are, what they consist of. Now we're going to talk about the calculations of those circuits. The first thing is you're going to see something called resistance. So resistance is essentially the degree in which an object opposes the movement of the electrical charge. And so what happens is, as that charge and current is flowing, the objects that are in the circuit are going to resist the flow so they can use them. Now, it is proportional to its resistivity and length, and when we say its, we mean the object or the wire, the battery, and it's inversely proportional to the cross-sectional area. Okay, so resistance is capital R. Resistivity we talked about in the first video is that rho, or the Greek letter rho. So directly related to rho, resistivity and length, and inversely related to the cross-sectional area. Now again, most cross-sectional areas are circles, so it's just going to be pi r squared. Now one thing to note is that this assumes that the resistivity is going to be uniform. So the densities or the resistivity is not going to change, the length isn't going to change over a position, the area is not going to change. But if you run into that random question in which the resistivity is or is non-uniform, okay, you can just simply use calculus, and that just becomes the integral of rho of L, so resistivity as a unit of, or as a function of length, dl over A. In fact, in our example problem, we're going to use this equation to solve for the resistivity of a material. All right, now all this is kind of combined together using current resistance and potential difference into what is known as Ohm's law. And so this is a mathematical relationship that shows the relationship between current resistance and potential difference. So the equation is current is equal to the potential difference over the resistance, but most commonly you'll see it written as V equals IR. Just like most of the equations we talk about in physics, the definition is usually as a ratio, but we just simply simplify it by solving for one of those factors. And what you see over here to the right, this includes power, which we'll get to here in a second. But if you actually search up on Google and you type in Ohm's law, they're going to give you like a triangle. It's going to, one of the, it's suggested searches is going to be the Ohm's law triangle. And this is, remember, this is just a way for you to help solve for it. And what you're going to see is in our picture, or in this circle, E is actually V. So anywhere you see an E, it's actually a V. Right, I'm not going to go through them, but you can see here's the Ohm's law equation. Here it is solved for resistance, and here it is solved for current. And so like that's what this little dial is about. Maybe beneficial if you went and searched for this and made a copy of it to put into your notebook or such, but that's just a suggestion. Now, some of the questions that you'll encounter will talk about, is the material ohmic, right? And so the way you look at it is notice that the ohmic relationship between V and I is linear, okay? Where the slope of that material or that function will be R. And the way to determine if it's ohmic, if you plot potential versus current and you get a straight line, it is an ohmic material. If you get anything other than a straight line, especially if it's curved in any way, like a parabola or a square root function or exponential function or cubic function, those are non-ohmic materials. And you can see, I did include some of the graphs to show you what ohmic means. You may also get into, like, in that first top left, a graph of, and it say which one has the greatest resistance, which one has the least resistance, or rank these in order from greatest to least, right? If it's flat, it's got a smaller resistance. If it's more steep, it has a greater resistance. Now, the resistance of an ohmic material And just kind of we explain this, all right, talking about how the resistance of the ohmic circuit can be determined from the slope of a graph of the current as a function of potential difference across the element. Now, the rate in which energy is transferred, converted, or dissipated by electric circuit depends on the current in the element and electrical potential difference across it. So the rate at which energy is transferred, that's power, or power equals I times V. And what you'll see is there's other equations in our little circle there that has, so right here, this is the power equation that I just wrote, right? But you can see anywhere else they have power solved for the other factors. So if I substitute in VR or IR into this equation, right? If I substitute I times R for V, I get I squared R. And if I substitute in V over R for I, you end up with V squared over R. And so there's just, again, you could see those equations show up on the our little dial there. Again, that dial would be beneficial if you went and actually made a copy of that to put into your notebooks. All right, so let's look at an example. So this is a coax cable, and coax cables are dielectrics because there's like, parallel plate, even though they're cylindrical, with a dielectric insulator, thus with a plastic jacket around them. And what we're asked to find is that we're trying to find the space, or excuse me, the resistance of the coax cable over the length of L, okay? And so we know it's going to vary based on the radius. And so what we're going to do is we're going to start with our rho resistivity equation. Now, because it's going to vary with respect to the length, we need to kind of rewrite this as an integral. And so we're going to say dr is equal to the integral of, sorry, not quite to that point yet. So we're going to say that rho dr over A, because the radius is going to vary, right? So we're going to start in the middle and go out, which then we can start, take the integral. And again, remember, whenever you have these functions, or you need to probably do some sort of integral, start with the original function and then figure out what is going to change, right, with respect to whatever, okay? And so the radius is what's going to change. And so this, right, and that's the L that we're talking about. So if you think about it, I've got, right, this coax cable, and the resistivity at different points is going to be different. So it's not the length, that L is not the length of the wire. That is the distance from the center out, okay? And so if we keep writing, so we know that R, right, is going to be the integral from, and I was writing this backwards earlier, it's going to be Ri to R0, right, because they call Ri the initial, and then R0 is going to be out to that dielectric insulator, of rho dr over, now the area is going to be, the cross-sectional area, or the length is going to be a cylinder, okay? So we're going to 2 pi RL is going to be our area. All right, so constant, 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 constant. So I'm going to pull all those out. So we're going to have rho over 2 pi L integral from the center out to our radius. And we're going to have a dr over R. Hi. So if you see anything change, you'll see at the end of the previous clip, it'll say technical difficulty. So we may backtrack a little bit, all right? So where were we? We were figuring out the resistance on the coax cable, but we're writing this in as an integral, right? Because it's going to vary. And so we had just taken the integral, or we're getting ready to take the integral. So we have R from Ri to R0, right? Ri is the center, R0 is where we're going out to, of rho dr, and the area, the cross-sectional area, is going to be a cylinder, right? Which is going to be along the central axis, not the ends, right? The end caps. So what happens is, right? Constant, 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 pull all those out. Very important technique that if you are just learning integrals, I would rewrite as much as possible. So rho over 2 pi L, and we're going to integrate dr over r from ri to r0. Now, dr over r is the integral of 1 over r dr. If you use the power rule, what you'll find is that you're going to get infinity because you have like 1 minus 1 is going to be 0, right? And so that doesn't helpful. But on the formula sheet, you'll see that the integral of 1 over r dr is simply natural log of r. Okay? And so that's where we're going to go next. So we have rho 2 pi L, and we know that this is going to be natural log of r evaluated from ri to r0. Again, we do upper minus lower. So rho over 2 pi L integral, or sorry, the evaluation R0 minus R, natural log of R. Again, we talked about this in one of the previous videos. Here's why you learn those exponential rules, because that just becomes the natural log of R0 over Ri. So our final answer is going to be rho 2 pi L natural log of R0 over Ri. So that right there is the resistance, right, in this coax cable. Again, there was a little screw up in the middle there. I'll make sure it gets all nice and neat. But that's the end of just simple Ohm's law and electrical power.